They don't make much noise, they rarely get seen, and most people never think about them. But giant industrial gears are the hidden muscle behind some of the world's biggest machines, from cargo ships and mining trucks to wind turbines and steel mills. These massive wheels of precision steel can be taller than a human and weigh several tons, yet they rotate with such accuracy that even the tiniest flaw could destroy an entire system. So how are they made? How do factories transform raw metal into perfectly shaped gear teeth that can move thousands of tons with flawless precision? Today, we're going deep into the world of heavy gear manufacturing, where sparks fly, machines hum, and nothing happens without serious engineering. 1. The blueprint. Every tooth starts with a plan. Before a single cut is made, every gear starts with an exact blueprint. These gears aren't just circular chunks of metal, they're precisely engineered to handle specific loads, speeds, and torque levels. Engineers work with powerful CAD software to design the perfect gear profile based on where it will be used. The shape of each tooth, the spacing, the pitch diameter, and even the curvature of the gear face must be calculated to the micrometer. These designs are reviewed by structural engineers and stress analysts who simulate how the gear will behave under pressure. Will it spin a wind turbine for decades? Will it endure the brutal load of an excavator bucket? The specs must match the environment perfectly because a single failure in an industrial setting could cost millions. Once the design is finalized, it's time to bring in the raw material, usually a huge steel billet or forged disc weighing several tons. 2. Forging the gear blank, shaping the foundation. The process begins with the steel itself, a solid piece either cast or forged depending on the gear's intended strength. Forging is the more common method for giant gears as it aligns the grain structure of the steel, making the gear tougher and more resistant to cracking under load. These steel blanks are heated in industrial furnaces to glowing orange temperatures, often above 2,000 degrees Fahrenheit. Then, massive hydraulic presses or forging hammers smash the glowing metal into shape, compressing the steel's internal structure and forming the rough dimensions of the gear. After forging, the blanks are cooled slowly to relieve internal stresses. They are then machined into near-perfect cylinders, called gear blanks, with exact diameters and perfectly centered bores. This step is critical. Any wobble or imbalance in the core of the gear would make precise cutting impossible later on. 3. Rough machining, turning steel into geometry. Now that the gear blank is ready, it's time to start shaping it. The first cuts are made on large CNC turning machines. These machines rotate the entire gear blank like a potter's wheel, while razor-sharp tools slice away material from the edges and faces. This step shapes the gear's outer rim, flattens its faces, and bores the center hole to exact tolerances. It's not the final finish, but it brings the gear within millimeters of its final shape. For gears that will have bolt holes or mounting features, those are drilled at this stage as well. Even at this rough stage, everything is done with incredible precision. The machines must compensate for heat, vibration, and the sheer mass of the gear, which often weighs several thousand pounds. Coolants flood the cutting area to keep the metal from overheating and to wash away metal chips as the work progresses. 4th, gear cutting, crafting the teeth with precision. Now comes the most iconic part of gear making, cutting the teeth. This is done on a gear hobbing machine or a gear shaping machine, depending on the size and type of gear. In hobbing, a rotating cutter known as a hob slowly moves across the blank, while both the cutter and gear rotate together in perfect synchronization. As the hob spins, it carves out tooth after tooth in a spiraling motion. This technique is used for straight, helical, or even bevel gears and can create hundreds of teeth with microscopic consistency. For gears that require internal teeth, like ring gears, shaping machines are used. These machines mimic the action of one gear turning another, cutting from the inside out with reciprocating tools. The cutting process can take hours or even days depending on the gear size. But when it's done, you're left with a perfect ring of uniform teeth, each one matching the next to a degree of precision that's difficult to imagine, considering the gear might be taller than a man. 5. Heat treatment, making the gear. Tougher than steel. At this stage, the gear looks complete, but it's not ready to work. The next step is heat treatment, a process that transforms the surface of the gear into a hardened, wear-resistant shell without sacrificing the flexibility of the core. The gear is placed inside a specialized furnace and slowly brought up to a very high temperature. Then, depending on the method used, it may be quenched in oil, water, or even gas to rapidly cool the surface. This sudden change causes the outer layer of the steel to harden significantly. The most common method for industrial gears is called case hardening. It creates a hard outer shell around a softer core, like a peanut M&M but made of steel. This makes the gear resistant to wear while still being tough enough to handle shocks and heavy loads. After heat treatment, the gear must be checked again for distortion. High temperatures can warp even the strongest metal, so it often goes through another round of machining to restore perfect shape. 6. Grinding and finishing. Smoothing. Every micron. Once the teeth are hardened, they still need to be smoothed and finished. This is where gear grinding comes in, one of the most precise and delicate steps in the entire process. A grinding wheel made of abrasive material is carefully run across each tooth surface to remove microscopic imperfections. This not only makes the gear quieter in operation, but also ensures perfect meshing with its mating gear. For gears used in high-speed applications like turbines or locomotives, this step is absolutely essential. The faces of the gear are also machined again to restore flatness and symmetry. Any imbalance or vibration at this scale can damage entire gearboxes. Some gears are polished for corrosion resistance or coated with special materials to handle extreme conditions like salt water or heavy dust. After final finishing, the gear is nearly complete. But before it can leave the factory, it still has to prove itself. 7. Inspection and testing, ensuring perfection. No industrial gear leaves the plant without rigorous testing. First, it goes through dimensional inspection, where high-tech measuring tools and coordinate measuring machines scan every tooth, face, and bore for size, angle, and roundness. These machines can detect errors as small as a few microns. Next comes surface testing. Engineers check for cracks, hard spots, and roughness that might not be visible to the eye. For critical gears, ultrasonic or dye-penetrant testing may be used to detect internal flaws. Finally, the gear is test-fitted into a simulated gearbox setup to make sure it meshes smoothly with its partner gears and doesn't produce excess noise or vibration. Only after passing all these checks is the gear approved for shipping, a towering masterpiece of metal that's ready to work for years, sometimes decades, in extreme environments. You may never see them, but giant gears keep the world running. They drive the cranes that build skyscrapers, the wind turbines that power homes, and the cargo ships that connect continents. Each one is the result of weeks of forging, cutting, grinding, and testing, not to mention decades of accumulated engineering knowledge. Next time you see a bridge lift, a turbine spin, or a factory hum, remember that somewhere inside, there's a gear doing the heavy lifting, quietly, relentlessly, and with almost impossible precision. If you found the process of gear manufacturing as mind-blowing as we did, give this video a like and subscribe for more deep dives into how the world's biggest machines and tools are made. And let us know in the comments what industrial component or machine should we explore next. Until then, keep your gears turning and stay curious.